Welcome to the deep dive. You've brought us a really interesting piece today. It's an article by Dr. Brian Keating titled Liar, Liar, Big Bang Denier.
That's the one. Yeah, digs into these claims by Eric Lerner, who's, well, he's really pushing back against the standard Big Bang theory.
And Keating focuses on Lerner's main point, which seems to be about lithium.
Exactly. Lerner's argument, as Keating lays it out, zeroes in on what he calls a problem with the amount of lithium we see in the universe. He's even calling it the final nail in the coffin for the Big Bang.
Wow, okay. Final nail. So this is specifically about lithium levels. Keating's article mentioned a recent study, didn't it? What's Lerner's angle there?
So Lerner's pointing to a 2024 study. They looked at lithium in this really old star in the Small Magellanic Cloud.
Okay.
And the key thing was this star had way less lithium-7, that's the specific isotope, than the Big Bang model predicts should have been cooked up right at the beginning.
Less than predicted.
Yeah.
And Lerner says this difference, this mismatch, basically breaks the model.
That's his claim, yeah. He argues it's a fundamental flaw.
Okay, so in this deep dive, what we need to do is unpack this. Does this lithium issue really, bring down the whole Big Bang idea like Lerner claims?
Or, as Dr. Keating argues, is there maybe more to this story, a bigger picture we need to look at?
Right. Let's get into it.
Absolutely. And Lerner, he uses some really strong language. Like you said, Keating pointed out final nail, comparing the Big Bang to Dracula.
Dracula.
Oh, yeah, it's quite dramatic. He's really hammering home how important he thinks this lower lithium reading is from just that one star.
But Keating's first response, reading his article, seems to be, well, hold on a minute. Let's not get carried away by one single data point.
That's a key part of Keating's rebuttal. He makes a really strong argument about perspective, right?
How so?
Well, he reminds us that the Big Bang isn't just built on one or two things. We're talking, tens of thousands of observations that fit the model.
Tens of thousands, okay.
So Keating's saying, should we really throw out this entire well-tested framework because of one measurement that looks a bit off?
Yeah.
Even if it seems statistically significant, it might be jumping the gun.
He had that analogy too, didn't he? Something about a really extreme outlier.
Yeah, that was interesting. He said, even if this lithium result was off by some crazy amount, hypothetically, 100 sigma, which, it definitely isn't. But even then, one super extreme outlier wouldn't automatically mean the entire theory is trash. It would mean we need to investigate like crazy, figure out what's going on, but not instant demolition.
That makes sense. You don't discard everything because of one anomaly. And Keating then brings up the successes of the theory, particularly Big Bang nucleosynthesis, or BBN.
Exactly. That's the other side of the coin. BBN isn't just about lithium. It's actually been incredibly successful at predicting the amounts of other light elements formed in the first few minutes.
Like what?
Well, things like deuterium, that's heavy hydrogen, and helium-3, helium-4, the main helium isotope. And yes, trace amounts of lithium-7 too.
And these predictions aren't just random guesses, are they? They're tied to something fundamental about the early universe.
That's the really elegant part. Most of these predictions hinge on basically one number, the baryon to photon ratio. The symbol is eat us.
Okay, one parameter predicts multiple element abundances.
Pretty much. It's like having one knob that sets the cosmic recipe, and it correctly gives you the amounts for deuterium, helium-3, helium-4. It describes the density of ordinary matter relative to photons back then.
So the fact that BBN gets all those right using just that one input value is, well, that's pretty impressive.
It's a huge success for the Big Bang model, yeah. Which makes the lithium issue more like an outlier within that success.
So lithium-7 is the known exception, the one that doesn't quite fit as well. But Keating frames it as like a normal part of science. Models aren't always perfect.
Exactly. That's how Keating sees it. No scientific model is ever 100% perfect right out of the box.
Yeah.
There are always going to be areas where the predictions and observations don't line up perfectly. The lithium problem is one of those puzzles.
A puzzle to be solved, not necessarily a theory killer.
Precisely. It doesn't just wipe out all the other successful predictions.
Okay, and then Keating adds another layer, right? What happens inside stars long after the Big Bang? Lithium isn't static.
Yes, this is super important. Stellar physics plays a big role. Because, well, lithium-7 is actually pretty fragile.
Fragile how?
It gets destroyed relatively easily inside stars. There are a few ways this happens. Convective mixing is when material churns inside the star, dragging lithium down to hotter core regions where it undergoes nuclear fusion and gets, well, obliterated.
Okay, so internal churning destroys it.
Yeah, and there's also direct fusion in the core itself, plus other processes that can deplete lithium from the star's surface over its lifetime.
So the amount of lithium we see in an old star today isn't necessarily the amount it started with right after the Big Bang.
Absolutely not. The star's own evolution has likely changed that initial amount, maybe significantly.
Which means seeing less lithium than predicted primordially doesn't automatically mean the prediction was wrong.
Exactly. It could just mean the star has processed and destroyed a lot of its original lithium. We need to account for that stellar processing, which is, complicated stuff.
This really brings up that contrast Keating makes, doesn't it, between how science usually works and how Lerner is approaching this.
Yeah, this point about scientific methodology, Keating emphasizes that, look, scientists expect anomalies. They expect things that don't quite fit.
Right.
And usually the reaction isn't burn it all down. It's more like, okay, this is interesting. What can this teach us? How can we refine the model? Is there new physics here?
It drives progress.
It drives progress, exactly. But Keating suggests Lerner's doing something different, taking this one issue and demanding we junk the entire standard model.
And promoting his own alternative model, plasma cosmology.
That's part of it, yes.
Yeah.
And Keating also notes, maybe a bit pointedly, that Lerner often ties these arguments into seeking investment for his fusion energy startup, LPP Fusion.
Okay. So a potential conflict of interest angle there, maybe.
Keating raises it as something to be aware of, the context behind the claims.
Right. So, okay, let's put the lithium aside for a second. Keating also makes sure to remind us about the other evidence, the big pillars supporting the Big Bang, like the cosmic microwave background, the CMB.
Oh, CMB is huge. Probably the single strongest piece of evidence. It's that leftover heat, that faint microwave glow from the very early universe, just a few 100,000 years after the Big Bang.
And it's not just that it exists, right? It's the details.
Exactly. It matches the predictions incredibly well. It looks like a near-perfect black body spectrum, just as predicted. And it has these tiny, tiny temperature fluctuations, little hot and cold spots that are exactly the kind of pattern the Big Bang model predicts we should see.
And we've mapped this with multiple missions.
Yep. CoTV first saw the big picture. Then WMAP and Planck mapped it in stunning detail. Ground-based telescopes like ACT continue to refine it. It's just incredibly consistent with the theory.
Okay, pillar 1, CMB. What else? You mentioned helium earlier.
Yeah, primordial helium abundance. BBN, Big Bang nucleosynthesis, predicts that the early universe should have cooked up about 24 to 25% helium by mass. And when astronomers look at the oldest, most pristine gas clouds, they can find places that hadn't been messed up too much by subsequent star formation. Guess what they see?
About 24 or 25% helium.
Bingo.
Raw.
Right on the money.
Oh.
Another major prediction confirmed by observation.
Okay, CMB, helium abundance, and the universe is expanding. That's fundamental too, right?
Absolutely fundamental. Edwin Hubble's discovery, and it's been confirmed over and over again with different methods.
Such as?
Well, the redshift of distant galaxies is the classic one light gets stretched as space expands.
Yeah.
But we also see it confirmed by studying type E as supernovae, these standard candles across the universe. And also by looking at baryon acoustic oscillations. These are like characteristic patterns or ripples in how galaxies are distributed on large scales, leftover echoes from the early universe. Even the patterns in the CMB itself confirm expansion. Multiple independent lines of evidence all point to an expanding universe.
So when you stack all that up, CMB, helium expansion, the general success of BBN, and then you look back at the lithium issue.
It puts it into perspective, doesn't it?
Yeah, it seems less like a final nail and more like, well, a puzzle piece that doesn't quite fit yet.
That's exactly how Keating, and frankly most cosmologists, view it. It is a real discrepancy. People call it the lithium problem. It's there in the data.
How big is the discrepancy, statistically speaking?
Keating mentions it's around a 2.5 sigma mismatch, which is, noticeable. It's not something you just ignore. But in particle physics, they often look for 5 sigma for a discovery. So 2.5 sigma is interesting. It warrants investigation, but it's not usually considered a crisis for a major theory.
And Keating's point is, this discrepancy might actually be telling us something new.
Could be. It might be pointing towards, say, gaps in our understanding of how lithium behaves in those very old metal-poor stars. Maybe stellar evolution is slightly different than our current models assume.
Or maybe something even more fundamental.
Or maybe something about nuclear physics or even exotic physics in the early universe we haven't figured out yet. Anomalies are often where the new discoveries hide.
Yeah.
So scientists are working on this. It's not being swept under the rug.
Oh, definitely not. Keating mentions several active areas of research. people are looking really closely at the decay of beryllium-7, which is produced in BBN and then decays into lithium-7. Maybe that process isn't perfectly understood.
Okay.
They're also studying how cosmic rays, high-energy particles zipping through space, might interact with interstellar gas to create new lithium, which complicates the picture, and running big computer simulations of galactic chemical evolution to model how lithium builds up or gets destroyed over cosmic time.
So lots of ongoing work trying to figure out this puzzle.
Absolutely. So recognize tension, and people are actively trying to resolve it.
Which brings us back to Keating's main point, really. Science uses anomalies to learn, not just to tear down established ideas.
Exactly. He draws that parallel with, say, flat earthers who might cherry-pick one optical illusion or ignore countless proofs of a round Earth.
Right.
Focusing only on the lithium problem while ignoring the mountain of evidence for the Big Bang, the CMB, helium, expansion, BBN successes, is kind of a similar approach. It's ignoring the forest for one slightly oddly shaped tree.
And he wraps it up with that little joke about lithium needs.
Yeah, his sort of signature dry wit, saying some people need lithium, medically, while others seem to need it to disprove the Big Bang.
Yeah.
Just highlighting the perhaps exaggerated importance being placed on this one issue by some critics.
So for our listener who shared the article, the big takeaway seems pretty clear. This lithium discrepancy, it's definitely interesting. It's a real puzzle scientists are chipping away at.
But it doesn't, erase the overwhelming evidence from decades of research supporting the Big Bang framework. It's not the final nail.
Which maybe leaves us with a question for everyone listening. What does it actually mean when a really solid scientific theory has an anomaly, something it can't quite explain perfectly yet?
Yeah, how does science usually deal with that? Think about the difference between saying, okay, this is weird, let's figure it out, maybe our understanding needs tweaking, versus saying, aha, one problem, the whole thing must be wrong. It's a pretty fundamental difference in approach, isn't it?
Definitely something to think about. And if you want to dig deeper into Dr. Keating's specific arguments and see his video on this, we have put the link in the description.
Yeah, it's worth checking out his full take. And thanks for sharing this topic. It's always good to dive into these debates and see how science actually works through these problems.
Absolutely. Thanks everyone for joining us for this deep dive.